Thank you very much. So if anything goes wrong, I blame it on the projector. I'll actually start with, so far so good. So I will actually start with, so I would like to define or discuss discrete analogs of analytic functions. But let me start first with an easier thing. Let me just sketch what's known about, or not what's known, but let's just introduce them, discrete harmonic functions. So we have a graph, say a finite graph. And let f be a function defined on the nodes. Say it has at least two nodes. And then we say that f is harmonic at a node if the value of f at this node is the average of the values at the neighbors. And otherwise, we say that it has a pole at this node. It is very easy to see that every non-constant function has at least two poles, because if you look at a point where it's maximized, well, it's a pole unless all the neighbors are also have the same maximum value and so on, and so eventually you find a pole. So either everything is constant or the maximum and similar the minimum value is a pole. There is a sort of well-known theorem, not hard to prove, which says that if you have a set S of vertices and you prescribe the value, sorry, that should be, well, that's, okay, that should be an R. And anyway, so there is a function defined on S, and there is a unique extension of it, which is harmonic on the new part. So let me sketch three possible ways to construct this extension, because I will just, at least I will need a couple of them later. So suppose that here is a graph, and here is the prescribed values, and I want to figure out what's the value of the function at this node V. And one thing I can do is I start a random walk from V, and until I walk until I hit somewhere S. So I get now a random point of S, denote this by Z sub V, and then I evaluate f at Z sub V, and the expectation of this is what I give to this node V, and it's very easy to see that this is a harmonic function. Okay, for 2 points, there's an easier way to describe this. It's the probability that hits the one before the other. If we have electrical networks, then again, what we can do is we can so we can consider the graph as an electrical network with every edge has unit resistance. And then we can keep these 2 points at the prescribed potentials, and then that will make some current flow through the graph, and then you just define the value of the function as the electrical potential at that point. And there's a third one where you can think of the edges of the graph as rubber bands, and you nail down the points where the value is given, the appropriate points of the ruler, and then let the rest find its equilibrium, and then the positions of these points along the ruler will give you a harmonic function again, sort of obviously. And there's a nice dictionary which you can use to translate various quantities between these three models. So, for example, there is effective resistance, RUV, between two nodes I and U and V is proportional to the commute time, and it's in the random walk model, and it's inversely proportional to the force that you will experience when U and V are nailed down. Okay, so this is all very well known. And these actually are useful because certain things are easier to prove in one model than the other. Now, okay, so now let me get to analytic functions. And they have been introduced as early as in 1944 by Ferran and then further developed by Duffin and others also a long time ago. And they were defined on a lattice. And the motivation to introduce these functions can be summarized as follows. So suppose you have some analytic function that you, but you're working in numerical analysis, so you really do all your computations on a grid. So one natural thing to do is then to restrict this analytic function to the grid, and then you do the computations on the grid. So for example, if you have to integrate along a path, along some curve, you approximate it by a zigzag, and then you do an appropriate discrete sum along this zigzag. The trouble is that this will not be independent of the zigzag normally. So if you, because it's easy to see by an examples that, I mean, it's only an approximation. If you do it on another path, you will get some other value. It will be close, but not exactly equal. So the idea is, why do this very simple way of restricting the function to the lattice points? Why not do some little bit more sophisticated way to discretize the function so that, on the other hand, integrals along path should be independent of the path? And that's what was the motivation here. And so we have an f which is defined on lattice points. That means, say, complex numbers where both coordinates are integral. And the assumption, one reasonable assumption is that if you compute the ratio of the difference of the function value and the ratio of the z's along one diagonal and along the other one, then these two values should be equal. Well, you expect both of them to be approximately the derivative at the midpoint. But we now require that this equality should hold. And then you can actually rewrite this equality. That's just an algebraic transformation. But the way, so you can rewrite it, but in this form it will be the sum of 4 summons. And the first summons sort of corresponds to integrating along this edge. I mean, the only way to, the only reasonable way, it seems, is that you take the average at the two endpoints and multiply it by dz, which in this case is 1. And then you do the same along this edge, except now you have to multiply by I because you move in the I direction, and then similarly. And indeed, this definition is equivalent to saying that when you go around, this integral will be 0. And that, of course, already implies that for any zigzag, and any other zigzag, as long as the function satisfies this for every little square that's between these two zigzags, the integrals will be the same. Now, there are some interesting discrete phonetic functions. If you restrict z to the, so if you want to get z, you can just restrict z to the lattice points. You can even restrict z squared to the lattice points, and you get a discrete analytic function. But if you restrict z cubed to the lattice points, that would not be good. But there is an analog of z cubed, which you get by using this.
If for the purpose of numerical analysis, why not just take the analytic function on the integer value, on the lattice, and then perturb them as little as possible to make it satisfy this condition?
That has been studied. There are many papers on that. But yeah. I will not go too much in that direction. So I just want to point out that the analog of z cubed, which you get by integrating z squared, is not the restriction of z cubed to the lattice. That would not be analytic. It's something a little bit different. Here is Okay, let me just, for another remark, come back here. So one thing you can see is that in this form that the differences along these two are only related to differences along these two. Now these are like the even points of the lattice, and these are the odd points of the lattice. So I could, for example, add a constant on each even point without changing this condition. That's a strange fact which does not correspond to anything reasonable in the continuous setting, but somehow in the discrete setting it comes up. So another way of looking at it, and this will be useful in our in a graph theoretic setting, is to rotate the picture by 45 degrees and then just look at the lattice formed by the even lattice points. And then I could say that, so an analytic function will have values at the lattice points as well as values at the squares. So, and then the relation will say something about the difference between an edge and the difference between an edge of the dual graph. So that will be a way to generalize it. But before doing this, let me say that this is more or less the first paper which contains implicitly this notion for general planar graphs. And so in this paper, Brooks, Smith, Stone, and Todd did the following. They studied decompositions of a rectangle into squares. Now, this is not, their goal was to find a square which can be dissected or tied with all different sizes of squares. They actually constructed such an example. But really the paper is much more interesting than just this single outcome, because it implicitly introduces this notion of discrete analytic functions. Now, since we have, everybody has to have animation here today, so let me bring up this. This is only, yeah, okay. So I would like to illustrate how they do it. So here is some planar graph. It happens to be the dodecahedron, but let me make it a bit more complicated by adding an edge. And now let's think of these two nodes, the two extreme nodes, as pinned down. And now let's think of the other edges as rubber bands, and let's see what happens. Well, of course, everything will collapse on just this segment, but I perturb it a little bit so that you can, not everything is on top of everything. So that's still, okay, so we know that this gives a harmonic function on here, but actually it also gives a nice tiling. Of a square by of a rectangle by squares, and the graph is overlaid. We can hide it if you want to see. So the idea is that the points now, I didn't change the vertical position of the points, and so they form this harmonic function in this direction. Now each edge corresponds to a square, and the point is that the side length of the square is sort of the vertical projection of that edge. So that's how I choose it. Now, if you look at a node, it will correspond to a let's look at a more well, okay, if you look at a node, it will correspond to a segment where there are some edges coming from the left and some edges coming to the right, and the corresponding squares just make up the length of that segment. So it follows that the same length is attached from the left as to the right. And from this you can sort of start here and move from left to right, and just fill up. So you see this point. This will have, once you have this square, you look at this point. There are two edges coming to the right. One gives rise to a little square like this because vertically it has a very small projection. The other one gives rise to a much larger square. And the two together will exactly match this square because that's the harmonic function. It means that the sum of these differences is 0. So the sum of the differences. So harmonic function means that the sum of fx minus fy over all neighbors y is 0, which exactly means that these squares match that edge, match along these edges, and so you get this. I think you can actually, let me open, where is the graph that they constructed? I should have it here. Okay. No. I think it's this one, sorry. Yeah, I think this gives the smallest known tiling of a square with all different squares. And this is the graph that it comes from. Okay, so this was their construction, but it's still not clear what it has to do with so I have to. Okay, so this is. So once again, the construction was the following. I think this is rotated by 90 degrees, but it doesn't matter. So suppose here is some tiling of square by squares. I don't assume here that they are different. You have to work to make them different, but it's just some example. We look at all these horizontal segments that are composed of consecutive edges of squares. Each such horizontal segment will be represented by a node. This was also represented by a node and so on. And now if you look at a square here, it has an upper and a lower edge that corresponds to two nodes, so I connect them by an edge. And this way I get this graph. And you can think of something coming up in from here and going out from here. That doesn't make much difference. It's not hard to see that this graph is planar. And now what else do we know about it? So first of all, every edge has a number, a certain number associated with it, which is the size of the corresponding square. So for example, this edge here corresponds to this square, and therefore it has a number 1. Now if you look at it, you can observe that these numbers form a flow, like there is 1 and 4 coming in and 5 going out, which corresponds to the fact that this 5 through that point is the length of this edge, and therefore there are some squares attached from above and some squares attached from below, and they have to have the same total edge length. So you get a flow on this graph, but it's not just any flow, because you can also, if I write to each node its distance from, say, the upper edge, I get these blue numbers, and then the flow value is also equal to the difference between these two numbers. Another way of saying this is that if I go around a phase, or any cycle for that matter, and I add up the flow values with appropriate signs, so as long as I go in the right direction, it's positive. If I go backwards, it's negative. The total sum must be 0 because it's just the total change in this potential, in this blue value. So this is a flow which also doesn't have a rotation around any face. One more remark about this is that we can also look at it from left to right, and it's easy to see that in that case you get the dual graph. but you get the same values on the edges, on the primal and the dual edge, because the square is a square looking from left to right, so it has the same edge length. And so you get also a flow on the dual graph. Now, in this Brooks, Smith, Stone, Tutt construction, this is all planar and has these sort of terminals. But we will be more interested in closing this off, and then you have to go to higher surfaces because you cannot do it on the plane. It's easy to see that. In the plane, you cannot. So the point is that this edge will. There's no way to. If I can try to draw it back like that, but that crossing will not have the right properties. So there's no way to have a rotation-free circulation in the whole plane, as we'll see. Okay, so now let me come to now the exact definition. And the exact definition was given by Merca in 2001, so fairly recently. So we look at an orientable surface, closed orientable surface, sigma with genus G. And suppose that there is a graph which is embedded nicely in the surface, by which I mean that all the faces are, or the interiors of the faces are homotopic disks. So the usual embedding. Now, we define a rotation-free circulation as follows. It's a function f which is defined on edges with orientations. So we can think of every edge having a reference orientation, and then with respect to this reference orientation, then given this reference orientation, it has a flow value. I may reverse the orientation, and that will just reverse the sign of the flow value. And the condition is that at each node, the total flow, if I orient every edge out of the node, is 0. That means that it's a circulation. And the rotation-free means that if I take any face and I look at the boundary of the face and orient each edge, say, clockwise around the boundary, and then I add up the flow values along the edges, that also should be 0. Sometimes it also is useful to consider a weighted version, which means that we sort of think that every edge has a length, Lij, associated with it, and then this flow condition along a face, the rotation freeness, has some coefficients here, these Lij's. Of course, I could instead take 1 over Lij and put them there. But so anyway, there is some condition like this. I will only need the weighted version once or twice, but mostly I will talk about the unweighted version, or the most results remain valid for the weighted version. So here is an example that such a thing can exist. It's a trivial grid on the torus. This edge, of course, is the same as that coming back. And, of course, you can replace 5 and 17 by any other numbers. It's rather boring, but we'll see that once the graph gets more interesting, then these functions also get more interesting. Okay, this is just some local. Let's look locally at the picture. So one thing we can do is, so the black values form, unless I made a mistake, I hope not, they form a rotation-free circulation, and it's somehow part of some big graph. It's just a small piece. Now, one thing I can do is I can start out with attaching a 0 here, and then increasing it along each edge as I go by the flow value along that edge. And then because it's rotation-free, that means exactly that if I go around, I don't get into any contradiction. So I can do this extension as long as I only go around cycles which are contractible in the surface. Of course, if I go around the handle of the surface, then there's no guarantee that it's working. So anyway, I can define these values on the nodes, and we can see that this 12, for example, is the average of its neighbors. So it's a harmonic function because the differences are exactly the flow values. So the flow condition at this point says that this 12 is the average of its neighbors. If it's not, yeah, I think it is. So these red numbers form a harmonic function, but I could not really use a harmonic function as a definition because there's no unique way to extend it over the whole surface. I can only do this locally. Or I could go to the universal cover surface, but then it would be, I would have to talk about infinite graphs and so on, and I don't want to go into that too much. Now, another thing we can do is to look at the dual graph and attach the same number to each edge of the dual graph. And that will be a flow because the flow condition at this point exactly means that the rotation-free condition, the corresponding phase held, and vice versa. So again, I can start attaching 0 somewhere and then extend these numbers. Sorry, I shouldn't have used green, but I can blame it on the projector. So anyway, it's sort of clear that in the same way as I got the red numbers, I get some green numbers here, which give a harmonic function on the dual graph. And so I have two harmonic functions here, and they are related by the condition that the difference along an edge is the same as the difference along the dual edge. I have to make sure that the orientation is consistent. So say the difference of the red nodes, you take, say, this minus this, then you go left, or right minus left, or whatever, to get the same difference. So you have two harmonic functions, and it's like the Cauchy-Riemann equations are satisfied. So the one-directional derivative of one is the same as the orthogonal directional derivative of the other. And that's why it's sort of natural to consider these guys as discrete analytic functions. And this rotation-free circulation is like the differential of a discrete analytic function, so we can call it a discrete holomorphic form. And in fact, that's a good way of looking at it. Now, you could do the same thing with complex values, and that's what Merca does. It wouldn't be essentially more general at this point because in that case, you would have to multiply by I, so the real part of the red numbers is only related to the imaginary part of the green numbers and vice versa, so you wouldn't... so it decomposes into two things of which are both real. Okay. Now are there such animals on every graph? And the answer is actually quite easy. And it's a discrete analog of what's called in complex analysis the Hodge decomposition. So we take the set of all vectors on the edges, and in the same sense as before, that if I reverse an edge, then the corresponding coordinate flips by, and then multiplied by 1, and then this I can decompose it into three mutually orthogonal subspaces. So what is A? A is null homologous circulations. That means circulations which are either just send a unit flow around a face, or I take linear combinations of these, and that's the null homologous circulations. B is sometimes called potentials. They would be functions which can be obtained by assigning some values to the nodes and then take the differences along the edges. And these two are orthogonal to each other because it's very easy to see. I mean, if you go along the circle, any flow around the circle, and you multiply the flow values with the differences, you get 0. But they don't span the whole space, and there is a third part which is orthogonal to them, and this is exactly rotation-free circulations, because it's very easy to see that being orthogonal to the null homologous circulations means it's rotation-free, and being orthogonal to the potentials means that it's a circulation. Now let's compute dimensions. The dimension of the whole space is the number of edges, which I denote by m. The dimension of this subspace A is the number of faces minus 1. Remember, it was generated by flows that are centered on one flow around each face. And there is one, if you add these up, because it's an orientable surface, I assume, I don't know if I told you, but anyway, I assume it's an orientable surface. So the last one follows from the other. So it's a linear combination of them. And it's easy to see that there's no other linear relation between these generators. So I denote this number of faces by f. So it's f minus 1. And the dimension of the potentials is the number of nodes minus 1, because I define them by assigning a value to each node, but I can shift. I add the same constant to each node. That wouldn't change the differences along the edges, so it's n minus 1. And from here, the dimension of this C is number of edges minus number of node minus 1, minus number of faces minus 1. It's just twice the genus. So the dimension of these rotation-free circulations only depends on the genus. It's twice the genus. So we don't have anything on a sphere, because it has genus 0. But we do have a two-dimensional space on every toroidal graph. We have seen this very trivial graph where there were indeed two numbers that we could vary, but that's true on any toroidal graph. You always get a two-dimensional space. So the dimension of rotation-free circulations is 2G. It's an important fact, as we'll see. Now, let me talk a little bit about the following question. We know that analytic functions cannot vanish on large set, where large say that it has an interior point or something. So the question is there any analog of this in the discrete setting? So if we have such a discrete rotation-free circulation, say, on a surface, what can we say about the parts where it's 0? So the first thing is that its size will not give the right answer. Let's look at the following example. So we have a graph, and in that's embedded in some big surface, but there is a planar piece. So this is a disk embedded in this disk part of the whole surface, and it's separated by number of points which is smaller than 2G. So now, I don't know, there could be very many points here, but the point is it's separated from the sort of topologically non-trivial part of the graph by fewer than 2G points. Well, I can do the following. First of all, I can contract this planar piece to a single node, and then I claim that I have here a non-trivial rotation-free circulation which will assign values, 0 flow values, to all of these edges that go out of this node. And the reason is that there are fewer than 2G of these edges, and therefore, I have a 2G dimensional space, so there will be a vector in that space which is 0 on all of these, but it's not 0 everywhere. So it's not 0 somewhere else, but it's 0 on all these edges. And now I can just pull this back. I assign outside, I keep this, and here inside I assign 0 to every edge. And so I got a non-zero, discrete holomorphic form, which is 0 on all edges here in this arbitrary large piece. So that looks like bad news. But it turns out that really this separating set is is what causes the trouble. And so here is a theorem. Suppose that F is a non-zero rotation-free circulation. I look at its support, subgraph where it doesn't vanish. I denote it by G prime. And let U be a connected subgraph that is such that F vanishes on all edges incident with U. So U is a part where it's zero, but zero in the sense that on all edges of this graph and also all edges going out of it. Then the theorem says that in that case, this U can be separated from the non-zero part by at most 4G minus 3 nodes. It's a result of Itai Benyamini and myself. The point here is that if we had 4G minus 1 here, then at least, and the piece was planar, then we knew that there was then we know that there is such a circulation which vanishes it. I don't know where the truth between 2G minus 1 and 4G minus 3 lies, but I'll come back to this. The question can be refined which separates these two cases. But, so at the moment, just let's say that we know that if it's separable by about 2G nodes, fewer than 2G nodes, then it can be a zero set. And if it's not separable by 4G minus 3 nodes, then it cannot be a zero set. So if it's well connected, then it cannot be a zero set. Yeah?
Does this go back at all? Can one guess at a theorem about analytic functions that suggests where the 4G minus 3 is coming from?
I'll show you sketch you the proof. Maybe, yeah, maybe I'll sketch you the proof. The 4G minus 3, it's topology. It's really, so here is an easy topological lemma. So take an oriented graph embedded in in S, of genus G, and for every face, let's walk around the face and count how many times we see an orientation change. That's some number AF. There's the orientation, so the direction of the edge. At the moment, there's no function on the graph. It's just the graph and an oriented graph. And similarly, I look at every node V. I denote by BV the number of times the orientation changes if I walk around the star of V. Sorry? So these are both even numbers, yeah. One could divide by 2, but maybe it would be more natural. And then there's this very simple identity that if I sum AF minus 2 over all faces and BV minus 2 over all nodes, I get 4G minus 4. And that's really just one line, because if I sum AFs and the sum of BFs, then every corner is counted exactly once. Because if the corner has 2 edges going out, I count it as a sign change along the face, and otherwise I count it as a sign change along the vertex. So every corner is counted exactly once. The number of corners is the same as the number of sum of degrees, so it's twice the number of edges. And from this is just rearranging and using Euler's formula. But this lemma will be very useful. Okay, so here is the last line of the proof. So I'll only sketch the proof of the theorem. I make an assumption that, so here is a big part of which is 0. I assume it's planar. That's a simplifying assumption. And I assume that there are no other zeros again. So to get the full proof, you have to work harder. But the idea will be, hopefully, I can make it clear from this. And I do just before that I contract this part to a single point. But now, of course, I have a flow. So now I have here a flow. I contract this part to a single point. So I have the flow still outside, and the flow gives me an orientation. So I reorient every edge so that the flow values should all be positive. So I get an orientation out here. And the edges going into this point, I orient alternately in and out. I think I made a mistake here. This should go the other way. So I alternate with the edges. And now I just count. So AF is at least 2 for every face, because what would it mean that it's 0? It means that the face is oriented all the same way, which would mean that it has a rotation. So in a rotation-free, so because the flow is rotation-free, I cannot have a face which is oriented all in the same direction, so I get at least 2 changes along each face. It's easy to check that it also holds here, because already this part had to produce those changes. And what do I get for the sum of BV? Now, if V is sort of a typical node, it should have edges going in and going out, so the orientation must change at least twice, so this is also non-negative. And there is this node here, which, on the other hand, has essentially as many changes along it as the number of cut points here. So it follows that the number of cut points is less than or equal to 4g minus 4, and we lose 1 because this may be odd, and in that case it doesn't alternate perfectly. So that's where the 4g minus 3 comes in. Okay, so so this is 0. Okay, good. Actually, there is a little newer work with Lex Schreiber, and we looked at the more generally whether you can describe which sets of edges can be supports of rotation-free circulations. And thinking about this, we realized that there are really 3 versions of this question. We can look at the case when we want it for every weighting of the edges. And in the first example where we had a low degree point, that worked for any weighting of the edges. It was an argument that didn't depend on the weights. Or the other interesting case, of course, the most interesting case is if all weights are 1, but that's the most difficult case at the same time because there can be strange numerical coincidences. And finally, you can ask whether there is some weighting at all for which something can be 0. And so here are the results. When it holds for every weighting of the edges can be characterized completely using matrix theory. I won't state the result. It's the usual kind of, I think, Irina called it Laman type thing. So for every subset of the edges, you count this and that, and it has to be positive. So anyway, this can be completely characterized. I don't know really any general result about this. Of course, it falls sort of between the two. And this is really a completely combinatorial question. It comes to the following. You have a map on the surface, and you want to orient the edges, but some edges you can leave unoriented. These will be the 0 edges. And then you want it so that every face should have at least 2 orientation changes, and every node should have at least 2 orientation changes. We think it might be possible to characterize when can a graph be oriented like this, but we couldn't finish. So this version is a completely combinatorial question, which seems to be interesting on its own right. So which graphs can be embedded in a surface with some edges labeled 0? When can you orient the graph so that each face should have an orientation change and each node should have an orientation change? Yes, if you have such a thing, then you can define some weighting, and with respect to this weighting, some discrete analytic function, which will be 0 there. Okay. A very special case of the results is the following. Of those results from the previous slide I didn't state, is the following, that if you have, first a notation, chi uv, I denote the incidence vector of an edge. So it's 1 on the edge, uv, and 0 elsewhere. Now this is in the big space R to the E. And remember that we decompose this into 3 mutually orthogonal subspaces. So we can project this on this third one. So we can project this on the set of rotation-free circulations, which is C, and I denote this by eta uv. Now, it's not so easy to see what this projection is. It's a rotation-free circulation, and if G is positive and the graph is reconnected and simple, then this projection is never 0. It's never the 0 circulation. Of course, we have to assume that the genus is positive, because for the genus is 0, then no rotation-free circulation exists other than 0. An equivalent, okay. Yeah, it's just a quick picture to show that that this edge here has never a flow in a rotation-free circulation. That's not hard to argue here, just using the symmetry of this little piece of the picture. So outside you can have anything, but you have this little thing here, and this edge must always be 0 in every rotation-free circulation, and also for this edge and this edge. So this shows that why we had to assume that the graph was reconnected and simple. Okay, and here is a better way of stating the same theorem, which says that if G is reconnected and simple and the genus is positive, then there exists a rotation-free circulation which is not 0 on any edge. So there is a everywhere non-zero rotation-free circulation. We'll see that this is actually a useful fact. Let me finally mention a strange identity. So there was this eta uv, which was the projection of the vector, which was 1 on uv and 0 everywhere else, and we project it on rotation-free circulations. And we look at the coordinate on itself. So how much flow does it contain? Well, because it's a projection, it's the same as the total length squared. And the identity is that this can be expressed as 1 minus the resistance in the graph between the endpoints of u and v, minus the resistance in the dual graph between the endpoints of the dual edge. So you can express this, somehow relate this to electrical networks. And as a corollary, we get that if G is a three-connected map, then the resistance between the edges of a graph and endpoints of an edge of a graph, and the resistance in the dual graph between the endpoints of the dual edge is, the sum of them is 1 if the genus is 0, and it's less than 1 if the genus is non-zero. Some funny fact. So now let me get back to just the torus. And let me relate analytic functions to the other words in the title. So here is some graph in the torus, and I have drawn it with straight lines, but it doesn't have to be. At the moment, this is just some abstract map. Now, one thing that I will need is to go to the universal cover map or it will be convenient. So this is just, I repeat the same pattern in a doubly periodic fashion. Now, here is a rotation-free circulation on this graph. I worked a little and computed one. It has a two-dimensional. We know it has a two-dimensional space. So this is one which is nowhere 0. And I can repeat it over the whole universal cover map. And of course, it will be doubly periodic. Now I can, okay. Now, okay. Now I can compute, forget about the 2 for a second. I can compute a harmonic function from this as we did. So you just start somewhere with 0, and then as you move along, you add the flow value. And this will be now a harmonic function on this whole infinite graph. Of course, it will be not periodic anymore, because if you move from this point to this point, there's no reason. You went along around a non-contractible cycle, so you get some non-trivial addition to this. Now you get 2 linearly independent such functions, because there are two linearly independent flows that you can start with. And now we can take the 2 coordinates. We can look at these 2 harmonic functions as the 2 coordinates. So I re-embed my graph in the torus, putting a point, not on the torus, sorry, this is the moment in the plane, putting a point at the where the first coordinate is the first harmonic function, second coordinate is the second harmonic function. So I started with 2 linearly independent rotation-free circulation. I sort of integrated them, so I got these harmonic functions, 2 harmonic functions, and I used them to define coordinates for the points. And and it's easy to see that actually this gives an embedding of the torus, so it will be doubly periodic if you define the period. So let me hide this. And so let's look at this nice picture. So you can see that, okay, so this gave me the positions of the nodes, and then I just connected the nodes by edges. And you can see, first of all, that this gives an embedding. And that's a non-trivial fact. I mean, why should this particular mapping of the nodes of the graph not produce crossing edges? But it's true. It's basically, it can be proved along the same lines as was a theorem of Tott about the planar similar construction. So you can use that. Second, you can also view this as a rubber band embedding. So for example, this node will be in the center of gravity of its neighbors, because both coordinates are harmonic, and that's the same thing. And therefore, if I consider these as ideal rubber bands, this point actually will be here. So this is so this picture actually gives an embedding with these ideal rubber bands. And you can also think of this as actually rubber bands on the torus, except you have to be careful, because this torus has the metric of C1 cross C1, so it's not the 3-dimensional torus. It's a 4-dimensional embedding of the torus that if you want to go metric, you have to look at. So these edges will be geodesics, but not on the usual donut. It's some other metric. So this gives an embedding. But it also gives another thing. We can do can sort of mimic the Tott, Brooks, and so on construction, and every edge will give a square, and the horizontal length of the edge will be the size of this square. And again, numerical errors are a little bit coming up here, but this is what we get from that graph. So this tiling of the torus. Now this is a torus because you can glue this with this and this with this. Now you may be on, okay, so one remark is that I took as a horizontal coordinate this, I started with a nowhere zero flow, which I mentioned that there's a theorem which says this exists, and that means that I get non-degenerate squares, so the size of every square will be actually positive. If the flow had zero values, then some of these little squares would actually degenerate. Now, it may be that you say that you don't like the fact that this is not a rectangle. And indeed, that is because I started with an arbitrary flow and another arbitrary flow, two arbitrary flows. Now, instead of this, you could work out which flow to start with so that this fundamental domain became a rectangle, in which case you can sort of, it's easier to imagine how to glue it together to a torus. That indeed works, except that in that case, the non-degeneracy cannot be guaranteed, because then it's uniquely determined which flow you have to start with. It's basically a diagonalization. You have to diagonalize a 2-by-2 matrix, and the eigenvectors will give the appropriate flows, and there's no guarantee that those don't have. In fact, it's easy to make examples. I did not draw the square version of this representation. I couldn't, it became too complicated, and the numerics became tricky. So anyway, as we see that we get all sorts of nice tiling results about the torus. So every three-connected toroidal graph gives rise to a whole family of tilings of the torus with squares, and there will be one which corresponds to the sort of the rectangular torus, but that may not be degenerate. On the other hand, there is one which gives all non-zeros too. And I think actually, well, maybe in 2 minutes I'll skip this. I just want to show you this more, because that was the motivation for starting this whole research. So suppose that you have a graph which is embedded in some surface, but you don't see the whole graph. You only see a small piece of it, a small window, like this red part. And the question is, there's some process going on the graph, some random local process. I will define it more exactly. Meanwhile, so something happening locally, it fluctuates a little bit, and I observe it here. And the question is, can I infer global properties of the graph from this local observation? So, for example, can I determine the genus? And so here is a construction which shows that you can. We call this the noisy circulator. And it has three. So at any point, the edges of the graph will have weights, positive or negative weights. And at some point, a node wakes up randomly, and it looks at the weights, and it sees that it is sending out more than it's receiving. So that's unjust. So it adjusts the weights, subtracts the same value, so that it restores the flow condition in itself. We call this node balancing. So a node wakes up, and it adjusts the weights around it to restore the flow condition. And then every now and then a face wakes up and looks and sees that it has a non-zero circulation and gets dizzy and adjusts the values around it to restore balance. So that's zero rotation freeness, and we call this phase balancing. And that would be too simple. So every now and then an edge wakes up, and it finds life too boring, and so it randomly adds or subtracts a value of 1 from its own value. And we call this edge excitation. And so this process goes on the graph, and it goes on, and it's an infinite process. But we only observe it locally. And the result is, okay, This is just technical issue that this has to happen with a frequency p. These wake up with frequency 1 with the same frequency, but the edges wake up with a much smaller frequency p. And so if no edge excitation occurs, so if that doesn't happen, then it's not easy hard to see that the weighting converges to a rotation-free flow. So even though, restoring the flow condition here may spoil it there, but in the limit, everything will be fine. Now
So if I write Sx, I guess I should have used a different letter, shouldn't I? So let me put a script letter here.